and is a self-supervised technique. And this is by me and Daniel. This is quickly the outline of the presentation, which is also the outline of basically the pipeline we followed for the project itself. At the start, I'm going to talk briefly about the dataset we used. This will be quicker than other times because it was not really the point of our project to extract to do a task on a specific dataset, but it was more testing a technique in general, and we used a very standard dataset. I'm gonna say in a bit to do that. Then we are going to talk about ResNet model. Then it's going to talk about ResNet model, which is the foundation of both the standard training that we use, supervised training, and it is also used in the VICReg model itself as a feature extractor. And then we are going to talk about the model, the VICReg model itself, and again about transfer learning, because often when you have self-supervised learning, the self-supervised learning is for learning representations and features, but then you have to move, if you actually want to use what you learned, what the model learned, you have to transfer to another model. And at the end, we are going to talk about the results we had. The aim of this project was, as I said, the study, implementation, and study of the theory behind VICReg. And to do this and to also test this technique, we do two simple experiments. The first one is done by comparing the accuracy, so the results of a training done in a standard way, so with a standard CNN, in this case ResNet, and backpropagation, stochastic gradient descent, etc. And training done with VICReg, so self-supervised learning and then transfer learning, with 100% of the training data that we had. This is the first experiment, is to see if the VICReg can keep with the actual standard way to train, and if it will give similar results, it means it is solid and can be used actually for some implementation. And the second experiment was to exploit what we actually want to use during a self-supervised task, which is using a significantly less labeled data. Instead of using 100% of the training labeled data, we're just using 20%, let's say, for the classification. And this will show how actually what are the true potential of this technique.
Can you explain better what it means and why to use 100% of training data, which, as you know, it's rather unconventional for machine learning?
No, I mean, this 100% is we are already leaving out the test data. So at start we see we have 50,000 images for the training set and 10,000 for the test set. What I mean with 100% of training data is that we are gonna feed 100% of our training set to the self-supervised learner, which is VICReg, and then the same 100% of data to the transfer learning task. Instead, when you do 80-20 split, let's say, you are using only 80% of the training sets to feeding, which become unlabeled data, basically, because for self-supervised, you don't need labels. And after you created some good enough features with the self-supervised technique, you use transfer learning, and you only need to train the last part. You only need to train the classifier head, and to train the classifier head, you use just 20% of data. And this mimics in a way what we can find in the real world. So we maybe have a data set of 10,000 images, but only 8,000 are 2,000 are labeled and 8,000 are not labeled. And we want to show that in this way it will work.
Does that answer your question?
Cool. Okay,
yes.
So this is quickly going through the libraries we use. Of course, we use PyTorch for every implementation of neural networks, and some classic libraries like matplotlib, etc. One important thing is we used Google Colab to do the computation, since our hardware was not powerful enough. And this is actually where you see the implementation of Colab while using GPU, basically. With the CUDA, you're using GPU instead of a CPU. So as I said, the dataset is a very standard one. It's called CIFAR10, which is a classification dataset. The train set has 50,000 images, and the test set has 10,000. And each image is a 32 by 32 colored RGB image. And the dataset is divided into 10 classes, which are which is images of planes, cars, birds, etc. When we load these images in the first part for the ResNet models, like the standard training model, which is kind of the control of this experiment, and also after with VICReg, we use a batch set of 128. This is because this is high enough that on average we'll have 10 images for each class, let's say, and it's also a power 2, which is common. And we also do some normalization, which is very basic normalization of images with parameters that we found on the literature, and they are actually the one they used also in the article, in the original article. This is just for numerical advantages. And this is how the dataset looks. We have a picture of a frog on the left, a horse and plane, and an ostrich. I think it's a kind of bird on the right. And these are, as you can see, they are very tiny images, and the resolution is very tiny. And this can be a problem, and will create some problems on the limitations that you have once you use very tiny images. But we can work around that. So now Daniel is gonna explain about the ResNet model, which is the CNN basically, and which is the standard way of training, and also it will be also used in the VICReg as a backbone, as a feature extractor. So I'm gonna pass to.
Okay, can you see and hear and everything? Okay, so we know the ResNet model, so let's just get into it. So most of this, to me, most of what we did was the application of this model. So we try to start at the most minimum part. So that was creating the basic block definition. So this is just the intricate part of the network that has to be repeated over and over again. And it's very simple. So we just use a convolutional layer, batch normalization ReLU, and then repeat. And then downsampling if necessary, depending on the stride. So that's all this is. Then it's applying it to ResNet. So applying it to the structure of ResNet. So this is just the definition of the class. This is some further information. And here's the implementation. So we're just initializing, because this is CIFAR based, we have to use a 222 structure for the layers. So that just means that every layer has two basic blocks. We have to use this architecture because of the size of the images, because once you get down to like a 1x1 height and width for the image, let's say with I think it's 64 channels, you can't go any smaller. You get errors. So this was one of the first things we discovered when we were implementing ResNet, was we were trying to use an ImageNet based structure, which is slightly different to this, and we had issues. So like I think there's 4 layers in the actual what's meant to be ResNet 18. So where we just have 222. So this is just the implementation. All examples of ResNets we've seen start with convolution, batch normalization, and ReLU, as well as max pool, and then you have the different layers appended with 2 blocks each, depending on this and depending on the stride, and you have your feature classification and your average pooling, and that's it. And then the only kind of cool thing is this lambda layer, which just helps in the downsampling, and it's just the format of it. but we'll see more on that later. And yeah, we know this. So here it is in a printed form, in a more visual form. So you can see the initialization, the first layer with 2 blocks, second layer 2 blocks, third layer 2 blocks, average pool feature classifier. So we chose parameters as per the article with number of epochs 80, learning rate 0.01, and we just set a seed for reproducibility. We use cross entropy loss, which is the standard loss function for multi-class. And we chose to use Atom optimizer, though in the article they use a more complicated optimizer because Daniele and I are learning. We thought it best to start from the most simple methods. So we used Atom, which is the go-to in my mind. Did I miss a bit? So this is one of our comparative models. So this is our training loop for using PyTorch. So we're getting all the images, we're moving into devices, and we're training it. So this is just we're just using our training data on the ResNet model, and we can use it as a comparison later on to our VICReg models. So it's just setting a basis. So this is the ultimate selection. So this is the go-to, and we're just comparing it using VICReg later. And we have the time, so it took 23 minutes. As Daniele said, we use the GPU on Colab. I know we had options to use the hardware at Federico, but with our application, we were just happy to use, instead of using a more complicated data set, which would have been nice, and applying it to there, we used a more simple data set, but yeah, and used Colab for GPU. Here's the results. Please, every one of these graphs are going to have wrong labels, so just please understand it's just a mistake. And we just didn't want to run it again and fix it because we ran it quite a few times. So you can see that the model's working, the losses are decreasing with epochs, and it's not overfitting, I would say, at this stage.
So basically,
it's a good
misplaced the labels.
Yeah, every one of them. We saw them when we were practicing yesterday. We saw it, and it's around 6 hours to run the whole sheet, and I was just like, oh my god! I'll just tell you, it's easier.
Okay.
Okay. So here's our training set accuracy. So using ResNet, we're getting 99.61%, which is really good, obviously. And then on the test set, we're getting 80.57, which is solid. So that's me. And then I think I'm passing back to Daniele, who this is the core subject now, the core topic, which is VICReg. So the reason we talk about ResNet is because of its implementation within VICReg. So that's why we initialized with that. But we set out to implement it at the most basic structures. So it's all ours, it's all everything. So we get a deeper understanding of the model and its implications. But anyway, Daniele, go ahead.
Yes. So now, until now, we talked about ResNet, which is useful in 2 ways. One way because it will be our control in the experiment, and the other way because it is actually a part of VICReg. Because what ResNet really is a feature extractor or encoder, sometimes referred to encoder, and then you got the last layer or last 2 layers that map the features, the feature vector, to the classes. And what we will use in VICReg, ResNet will be used as base as only a feature extractor. So we only care about the features at the end. But let's talk a bit more about VICReg itself. As with also most other recent self-supervised methods, this aims to produce, as I said, good image representations, which is basically the features, the extracted features of an image. And they typically split into 2 categories. Some produce global features like VICReg itself or also others, which are features about the whole picture, while others focus more on local features, which are very useful for image segmentation. while in the case of VICReg is more useful for image classification. And almost all recent approaches rely on what we call a joint embedding, which is a particular architecture on which we have two paths, the top path and the bottom path, which are often symmetrical. And
It might
they
be
have
worth showing the, sorry, Daniele, it might be worth showing the image here.
yeah, I'm
of
gonna show
You know, I know,
yeah.
I know. It's just when you're talking about top and bottom, it makes it a bit more
Yeah,
understandable. Sorry
it's
to
something
interrupt.
like this. Yeah, you're right. Something like this. You got the top path and the bottom path, which are two different networks. F theta in this case is an encoder, which is actually the backbone of the ResNet. And this means that we are gonna give the network two inputs, but these two inputs are gonna be created by the same single inputs, which is an image or a batch of images. And you basically you take an image and you create some two transformations which are different. One goes to the top and one goes to the bottom. And the aim of the whole architecture is to create similar, if not if and it is better if they are identical features on the top and on the bottom, which means that the encoders can tell, okay, this is slightly different than another thing, but they mean the same thing. And this means that they learn good representations. But this can also give problems because there's the so-called collapsing problem. This happens when the two architecture, the top and the bottom one, simply don't care about the input you give them, but produce always the same features for any image. And this is good for them theoretically because they produce by producing the same features, the difference will be always zero because they produce the same feature vector. But this, of course, is wrong because you don't gain any knowledge about the pictures in this way. And this is where VICReg comes, and VICReg, as well as other techniques like this, deal with this problem with a custom loss function. The loss function in this case is composed of three parts, but we'll see shortly about what are these three parts. And basically, it works like this. Let me, maybe it's better if I have the whole picture of what happens when I give something as an input to the architecture. So you give as an input a batch of images, which is called I in this case, a batch of n input images. These images, each of these image is transformed by some transformation, which is sampled from a distribution T. So we had transformation T, small t, sampled from a big T distribution of transformations. And the important thing is that on the top and on the bottom, you have different transformation, even if they are sampled from the same distribution. But they need to be different on the top and on the bottom. And this creates two batches, one X on the top and one X prime on the bottom, which are batches of the same images, but they are kind of distorted version of the original input. These batches, the top batch is fed into the what we call encoder, F theta, which is basically just a ResNet without the last layer. So it's just something that creates a representation vector Y, and same thing below. And then the encoded the features, the feature vectors are fed into what we call an expander H. An expander is basically a function, a nonlinear function that maps to a high dimensional spaces. In this case, it goes from the dimensional space of Y to the dimensional space of Z. And this has two purposes. One is to eliminate, this is proven to eliminate all information that is non-important and dissimilar between the two different feature vectors. And it's also proved that it is useful for decorrelation, because once you get to Z and Z prime, which are called embeddings, if you decorrelate features in Z and in the Z and Z prime space, this helps with not only decorrelating features also in Y and Y prime, but also by removing dependencies more than correlations. And finally, we get these two embeddings, Z and Z prime, which are embedding vectors of the same image, the same images that were in the input. And on this, finally, we calculate the loss. The loss will be a weighted loss that takes into account three parts, as we can see shortly. Basically, the first one is the variance term. This is what we use to combat the collapsing problem. This basically means that we are doing a max, which is just a ReLU, actually, rectifier linear unit here. And this means that we are pushing the two embedded vectors, Z and Z prime, to have variance of gamma in this case, but gamma is always put almost always put at 1, and we also put it at 1. This means what we really want is that the vectors have a variance of 1 or a variance of gamma, thus not permitting to the architecture to give always the same answer, because if it's always the same answer, the variance will be 0. While instead we push the loss to be greater than 0, and it will be less if the variance is near gamma. So we are pushing the variance to be gamma, and this gets rid of the problem of the collapsing problem. The second term is actually what is the core of the loss function, which is takes Z and Z prime as inputs, which are the two different embeddings of the same picture, always remember. And we want, of course, this to be equal in theory, but we want this to be similar in general. And this is just done by doing a Euclidean distance. So it will say if they are very distant in an Euclidean metric, then the loss is very high. This forces the two embeddings to be similar. And the last one is the covariance term, which is useful for decorrelating the features of the final embeddings, which, as I said before, will decorrelate also the features in the feature vector level. And this is done by just pushing the non-diagonal terms of the covariance matrix, which is standard covariance matrix. And it's pushing the off-diagonal terms to be 0. And the overall loss will be this one. So given a batch of embeddings Z and a batch of correspondent embedding on the bottom Z prime, you're going to have a variance term, invariance term, sorry, weighted by a lambda factor between the two, plus the variance term of Z and variance term of Z prime, of course, because both the variance and covariance terms only act on one of the two embeddings, so you have to include both. So at the end of the day, you do a weighted sum of these three terms to have the final loss. And the parameters that you're gonna use have to be optimized, of course. And we see what we used. Another thing, as I said before, an important part of this whole pipeline is the transformations. This means that every time we get an input, an image as input, we are going to transform it on the top and on the bottom. Some of these transformations, this is all the transformations we used. And one is the random resize crop, which is basically a crop somewhere on the image and then resize in order to make it consistent with the dimension of the architecture. And maybe the image gets horizontally flipped, or you apply some color jitter to the image or some grayscale. We also tried blurring with Gaussian blur, but it was not really useful. In fact, it was harmful because the images are already really tiny and really broad themselves. And then you can do some solarization. These are basically just the applications. Of course, you have to, when you define on PyTorch, you have to define the top part and the bottom part separately, even if they are the same. And this is just functions that are useful. And this is the same thing as I showed before. I did an error. Yeah, I must have put a space somewhere sometime, but it's the batch size is the same, and we just create the train set, train loader, test set, test loader, and we can see here some of the images. You see, this is the top path, this is bottom path. The frog image is not really a lot recognizable, but you can see it's flipped horizontally, and also the color is changed. The car is more easy to see. It's flipped and the color is changed. The ostrich basically it became a negative. And on the last one, you can really see the random resize crop, because in the first transformation, the image is cropped on the top, and in the second is cropped on the bottom. So this is just how we define the projector, which is the expander I mentioned earlier. And it's just the function we use for the covariance term, the off diagonal terms. So this will be our class that we implemented. The first two you already saw before, and it basically takes everything we need to create to instantiate.
Can you avoid the scrolling back and forward?
Oh
Just,
yeah. I'm sorry. Yeah, it's basically all you need to instantiate the class, the embedding, which is the output dimension of the ResNet model. So it's the number of features we're gonna create through the encoder. And num features is instead the dimension of the embeddings, which is the Z that I told about before. Then you have to, one important step is you have to set the FC, which is the last two layers of the ResNet model, to identity, because as I said, you in this case, in this time, you only care about creating the representations. You don't care about classifying, but you want to create good representation. At the end of the day, that's what self-supervised learning methods do. They learn good representations of images. And then forward is just the forward loop to get to the output from the input. The three parameters were chosen from the literature, from the article, which are 25, 25, and 1. And this is basically the forward. In the forward, you see everything I showed you before in the picture, but maybe here is a bit more complex to follow. But you got the projector, which is the expander, and the backbone, which is the ResNet model, the encoder. And everything here is basically what I said. So MSE loss is actually the invariance term, the one that minimizes the distance between the top and the bottom representation. And then these are useful for the other parts. So now we know how VICReg works. And we are still at self-supervised level. So this means that we learned good representations of the images, but how can we actually use it? And in order to use this representation, you have to transfer this knowledge to another model, and to train only a small part of that model in order to use it. And Daniel will keep on with the explanation here.
Okay, thank you, Daniele. Yeah, that was great. Like that's like the core of the project is this. Again, I got an easy part, so transfer learning. We know transfer learning, so let's get to it. Okay, so to me, transfer learning is just it's the downstream task. So you have all the training models where you create your representations of the self-supervised model, and the whole purpose of that is for a downstream task. It was first thought of in 1976 by Bozanovsky and Fulgos, and yeah, it's just a useful application to take the created feature representations and apply it again. This is an example of it. So you take your model, you do your first training, and then you reapply it to a new task. This is just a simple visual representation. So we talked about our plan for our experiments. So I think you understood that from before, so I won't reiterate. But yeah, 80% training will be used on the 100% will be used for both the classification head or the classifying the downstream task and the shift space. So in this section, we'll be using 100% of data again to train the new head, and we're going to use 100% here. And it was just a choice of ours to do so. And then in the second experiment, we'll have 80% of training used here and 20% used here. Okay, experiment 1. So all code, we've seen the training loop. It's the training loop again. So the main thing I can talk about is the times. This is one of the reasons we didn't want to run it again. So it takes 2 hours to train this model for 80 epochs. It's all the same as before. Nothing new. Here's the loss function, again, the error with the axi. So you can see this is the training loss for training the VICReg model on 100%. So we could have gone longer, but for fairness of the experiment, we kept all at 80 epochs, which I think was a good balance. This is how we save our model. So we reload it later, the weights and biases, but we'll see that, but this is just how you save it. So it's very simple. This is us loading the VICReg model, or the backbone more particularly. So just grabbing it from your location, just taking just the backbone, like this dot, it makes it so simple. Like just this dot type of labeling. This is how you freeze the weights. So we froze the weights of the trained representations, which speeds up running times and everything. But yeah, so this is just how you do it. We added a classification layer, feature classifier, and we put it to device. And here you can see the summary. But most importantly, you can see that our freezing weights has worked because we have a total of 172,000 parameters, but only 650 need training, which aligns with the last linear layer, last dense layer that we added. And then we're back in code. So 19 minutes to train the classification head on the 100% data. Here's the graph. So again, yeah, like you could probably stop earlier, but we just kept it fair. The test accuracy, train accuracy was 74%. So that compares to the 99%. So a bit of a drop off from that, but it's to be expected. And then for the test accuracy, very similar. So still 74%. So just a difference of 0.2, which isn't horrendous, isn't large, isn't bad. It's a bit lower than 80%, but the comparative difference between the two, the training set and the test set, is very similar. And these are generated, so we can compare it when we do our experiment 2, which is essentially creating a self-supervised situation. Okay, experiment 2. So we've just got the graphs here, just the bare bones. So very simple. You can see the training of the VICReg with 80% of data. And then you can see the training of the head with the 20% of data. It's got the same name because we use that as the name of the model, but it should say 20. So you can see on the training set, you had 73% accuracy. So just 1.6% lower. So pretty good. And then same for this. So 72.67. So by losing 80% of training data for the classification head, we only lost 2%. So our model's doing great. This is a great example of the power of this type of method and the importance of self-supervised learning, and just in terms of time saving, not having to label all the images, but still being able to create the feature representations. Here's the results summary. So we have the overall times. So as I said, well, we didn't get to see this, but it was again 2 hours. So just a little bit less in terms of training time because of the smaller training size. And then you can see the accuracy and the difference. So these are very similar. They're approaching, like they're not reaching ResNet, which is like, 100% supervised. So that's to be expected, but you can see that it is comparable, and we are learning the feature representations using the VICReg model. And that's the positives. Yeah, comparable, it's robust, and it's excellent. Yeah, we're very happy with this result, in all honesty. Yeah, negatives, computing time's long, but that's just what it is. It's, you know, we're training 172,000 parameters. Give us a break. You know, it takes a long time. Yeah, we had limited architecture to decipher 10. This was because of using a simpler data set, we were forced into using a simple architecture for our ResNet model, and that's just what it was. This isn't optimized. It is just using, you know, standard parameters just to give a good understanding and a good representation of what's going. Yeah, we had multiple times when we ran out of GPU on when training a model, because you only get like, I think, 12 free hours, 10 free hours. So if you train it once and you make a mistake, you can't train it again. So Daniele and I would have to like take turns using our collab to do it. And future improvements, future applications. So the where you would want to go with this project, we'd want to use a different data set, ImageNet. We can try segmentation with the Pascal data set with VICRegL. So using the segmentation. We could try more transformations on better optimizers. So we looked, obviously, we used a lot of the code for VICRegL, and we could see what they'd implemented, and we could see that the complexity of it, and these are possible applications. Also for the optimizer. Yeah, this is, I think, the main. Oops. This is the main last task, which would be finding what is your minimum, like, because you want to find the minimum labeled data that still gets a positive result. So you could find that point, which I think would be the continuation of this project. Yeah, increasing epochs, posing stopping conditions, you know, and then a really cool thing you can do is you can free the network of the Siamese architecture from sharing weights. So you can have independent weights. You can do different type of experiments in there. We just, again, we followed the guide of LeCun's article on VICReg, and we used the same weights as they had done, but there is the possibility of that. And then there's the very cool thing, which Daniele from the very start wanted to work on, which was doing multimodal inputs. And that means you can have completely different architecture and everything, which is I think a really great innovation. But that's it. That's what we got. Do you have any questions?